Hey there, everyone. Today we're going to balance a redox reaction in acidic conditions. Now let's cover these 7 steps that will help you solve these things in a fairly efficient manner. So first, when we're balancing a redox reaction in acidic solution, we will write half reactions, just like in other methods for balancing redox reactions. 2, we'll balance elements other than O and H. 3, we will then balance oxygen atoms by adding H2O to the opposite side of the equation. Number 4, we'll balance hydrogen, including the newly added H2O, by adding H plus ions to the opposite side of the reaction. Next, number 5, we'll add the charges on each side and balance that charge with electrons. Next, we'll balance the number of electrons on each side of the reaction by multiplying each half reaction by a coefficient so that we obtain the lowest common multiple between those electrons. It's a lot easier understood as we do it than it is to understand as I say it, if you haven't done this before. And then lastly, number 7, we'll add the half reactions, canceling out both the balanced electrons and other common terms there. And I know you've probably seen this before if you've been talking about any kind of oxidation reaction. Let's review. Oxidation is loss of electrons, and reduction is the gain of electrons. Okay, so to review, just one simple little half reaction here. Let's see, iron here is going from neutral iron to 3 plus iron. What does that mean? We have to look at its oxidation state to know if it was oxidized or not. So here it goes from a neutral species, which is 0, to 3 plus, which that means the species is a 3 oxidation state, positive 3. So that means that it went from 0 to 3, and as I've written here, it increases. And that means it was oxidized, right? Because oxidation is a loss of electrons. Electrons are negative, so if they are lost, something's going to become more positive, or the oxidation state will increase. Therefore, it is oxidation. All right, now alternatively, we have copper plus going to copper solid. So the oxidation state of that is going from a positive 1 to 0. Now we can see that that number, that oxidation state, is decreasing. So it's going from 1 to 0. That means it had to gain electrons, right? Because reduction is gain. So that means it gained electrons. If reduction is gain, it gained electrons, and thus the oxidation state decreased. Okay, so that's a simple review. Now let's actually balance a redox reaction in acidic conditions. And so it's important we just stick to our steps here. This can get really convoluted if you don't do that, or if you try to skip steps. Some people can do it in pieces like that, but I recommend you stick to these, follow these steps if you're just learning this, and it'll be a lot easier for you. Okay, so first let's find out what was oxidized, what was reduced. Now, you may just get asked about that and have to identify a species that was oxidized or reduced, right? So let's examine chromium first and figure out what's the oxidation state of that. I'm just going to write this below all these oxidation state. Now, if oxygen is usually 2 minus per oxygen, times 7, this is 14 minus 14. And the whole thing is 2 minus. So that means that that chromium has to account for positive charge to go from minus 14 to 2 minus. So that's plus 12. That means both of these chromiums must be plus 12. So 12 divided by 2 is 6, right? So I'll just write 6 times 2 there. It's supposed to be 6 times 2. So each chromium is oxidation state of 6. So let's go over here and examine this N. If O again is minus 2 per, there's 2 of them. That'll be a total of minus 4. Hydrogen, in most cases, is going to be plus 1. There. And now we have a plus 3, or a minus 3, excuse me, for everything but nitrogen. And so that will have to balance it out because the species is neutral. So that means that nitrogen must be plus 3. Now this chromium ion is pretty easy. That's just going to be another plus 3. And now let's check this nitrogen. So this O again is usually -2 per. That means 3 of them will be a -6 charge. And it needs to get to -1 overall. So that means that N must be +5. So now let's look. If oxidation is loss, what lost electrons? We just said it must be the thing that went more positive or the oxidation state increased. So let's check that out. Chromium went from 6 to 3. That's a decrease. Let's not go for that. N went from 3 to 5. That's an increase. So we'll write the oxidation half reaction first. Okay. Now let's write the reduction reaction, half reaction. And it must just be the other thing, right? The chromium. But if you look at chromium's oxidation state, what happened to it? It went from 6 to 3. So it went down. And to go down, it must have gained electrons, right? Okay, there are half reactions. Now let's balance the elements, not oxygen and hydrogen. So everything but hydrogen and oxygen. Allow me to rewrite. So let's balance this. Everything but hydrogen and oxygen. It looks like the N's the only other thing, and it's already balanced. All right, moving on to the other half reaction. So this one we said was going from 6 to 3, so that was our reduction reaction, right? But let's balance the CR. So there's 2 over here, and now there's 2 here. So now that's balanced. Keep just following the steps here. Here we have add H2O to balance oxygen. So now we're going to add H2O here. So we have 2 oxygen there, 3 oxygen there. So we're going to need to add 1 water because it has 1 oxygen on this side of the reaction. Go down here, 7 oxygen, 0 oxygen. So we're going to need 7 waters over here. So let's just rewrite them and add the waters in. There's 1 water. Okay. So the oxidation half reaction now has oxygen balanced. And now let's do the chromium half reaction. And we said the right side on that one needs 7 waters. Oof. That's a lot of water. So now that the oxygen is balanced, let's keep going. Now let's balance hydrogen with H+. So check this out. We got 1 hydrogen, 2, 3 hydrogen, and 0 over here. So we're going to need 3 hydrogen over here. Let's check this one out. 7 times H2 would be 14 hydrogen. So we're going to need 14 hydrogen on this side. We said we need 3 hydrogen, 3H+. Now let's balance the redox one with hydrogen. And we said we need, because we added 7 waters to the right, we'll need 14 H+ on the left. My. That's a lot. Now just write all the other species out. Those haven't changed yet. All right, step 4 is done. Now, just move to step 5. And you see I've already just transcribed the prior step. That's all. It's ready to just add the electrons onto, and I'll do those in a different color so you can tell. So we're balancing the charge of the electrons. And what does that mean? Now we're going to add up the charges on each side and make sure that the charge is all balanced from left to right on each half reaction. So first, let's add up the charge on the oxidation reaction here. Everything's neutral. So the charge is 0 on the left. Over here, it's not the case. 3 plus, so that's a plus 3, and then a minus 1. So plus 2 overall. Plus 2 overall to start. So how many electrons does it need to get to 0? 2. So that'll have plus 2 electrons. Now let's check out the bottom. So that's 14 plus on the left and a 2 minus. So that's plus 12. Plus 12. Then on the right, what do we have going on there? We have 2 times 3 plus, which is 6. And water is neutral. So the left looks like it needs to go minus 6. So 6 electrons. So that's a step, and we call it balancing the charge with electrons. You may hear that worded slightly different, and that's okay. So now we're going to balance these electrons by multiplying half reactions by a coefficient. So I'll show you up here. So we need the electrons on the left, 6, and the electrons on the right to match, but they don't currently because on the right we have 2 electrons. So we need those to match. So what we do is multiply the whole half reaction by a coefficient to get the lowest common multiple between the electrons. In this case, 2 and 6. So therefore the lowest common multiple is actually 6, since 2 is a factor of 6. So all we need to do to get the correct number of electrons for the oxidation reaction is multiply this whole thing by how much? To get 2 electrons to 6, we'll multiply by 3. The whole thing by 3. And I'm just going to rewrite it down here. Now I'm just going to rewrite step 5, but multiply by that coefficient that we just determined. That whole oxidation reaction multiplies by 3. Okay, you just took every coefficient from that oxidation reaction up there. And then since we didn't have to do anything with the bottom reaction, with the redox reaction, we essentially multiplied it by 1, we can just rewrite it. There we go. And now let's just check that the electrons are the same on both sides. So 6 on the right. And then I forgot to add that 6 electrons there, 6 on the left. Okay, so now for step 7, we're going to add the reactions, and we need to cancel out the common terms. So the electrons should always be in a common term, because that was the whole point of the steps we just did. There we go. And now let's cross out any remaining common terms. So there's no common terms with this. How about water? Yeah, there's some common terms, but we have 3 on that side, 7 on that side. So that 7 is just going to change into 7 minus 3, which is 4. So now I just wrote there 4H2O instead of 7H2O. We just deducted those 3 from the left. But all of those are consumed, right? Or all of those are canceled out. And then we have this 14H plus and 9H plus. So now let's cancel those out, leaving us 5H plus on the left and canceling out completely those 9H plus on the right. Now I don't see any more spectator ions, so let's rewrite the balanced equation. Now you're just filling in everything from the left and adding it together, and then everything from the right and adding that together. There we go. Plus, I'm running out of room here. There we go. So that's our balanced equation. And notice nothing that was crossed out made it down there. Everything else did. So I hope that was helpful. Make sure you go ahead and review all of the different types of redox reactions, and make sure you're also fairly skilled at doing them so that you can do them on exams in a prompt amount of time. Remember, it's a lot to go through on exams, so make sure you can do this fairly quickly. And you have to practice these quite a few times to get used to doing those steps. As you can see, the steps vary a little bit based off the different types of redox reactions. So make sure you master them all, and life will be a lot better on exam day. Take care.